Welcome to the Buildings and Air Handling lecture in week 12. Last week we did the first part of airflow, and you can always find the information at least partly in the textbook Unit 24, Chapter 2. Today we're going to continue that topic, which is airflow, and delve into the last two, titles. One is the fans and blowers, and the other is the calculations of RPM for pulleys, different sizes of pulleys. So I'm going to share with you what I've captured during the CMPX show. I hope you guys had the chance to visit the show. Uh, it is held twice, or I mean, once in 2 years, and it is also the only, the biggest HVAC trade show around in this area. So, if you want to, make connections, get to know people, maybe hand out some resumes, in a couple of years they will hold another one, I'm pretty sure. So I went and I took some images because I thought these were interesting and they are relating. So the topic that we're going to cover today, the first part at least, is blower types and uses. As you can see, the book has divided the blowers into mainly two parts. One is axial fans, and it has a propeller or tube axial or vane axial type. And then there's the centrifugal blowers that can have blades that are straight, or blades that are forward curved, or blades that are backward curved, or blades that are backward curved but have airfoil shape. So let's start with what was on the floor in the exhibition. This is what you can call a propeller blade axial fan. So one thing about these is that they are simpler to build and operate, and sometimes they are cheaper, although this one here is not necessarily the cheapest. As you can see, this is modular, so this particular fan blades hub here can accommodate three, so you can have one, two, and one, two, and three blades, or you can have six, as in this example here, one, two here, and two here, and two here, or you can even add, the third in a group, so they become 9 blades. The important part of this um, information is that when you add blades, you are adding capacity to this blade assembly to move air. Any blower, any fan is defined by its capacity to move air, because air, yes, it is light, it is not heavy. Still, when you're moving thousands and thousands of cubic feet per minute, you are doing work and consuming energy, and therefore you have to always consider, that little motor at the back. This is not little, actually, this is a big motor, but the motor that is sitting at the back and trying to convert that electrical energy to kinetic energy. And the amount of energy that is being used is directly proportional to the amount of air that is being moved as a rate, that is per minute or per hour or whatever the rate that you are using to measure. So the horsepower of the motor is supposed to correspond to the amount of power that is needed to do that work at that rate, moving that air at that rate. So you can see here, for example, if you go and read a little bit the details. First of all, obviously fans come in different sizes, but look at this CFM ranges. So you can apparently move up to 75,000 cubic feet per minute. That is not a joke. I would say that is a huge fan. And here are different, applications for it. So what I'm saying is that the amount of work that these fans do is due to the weight of the air that they are moving and the resistance that airflow is experiencing. Now, there's no duct here. And by the way, propellers should never be duct unless they are designed to duct. If you put a duct here, that what will happen is obviously you already know now from gas piping design and vent sizing and stuff like that, that the flow of fluid in a conduit is going to experience resistance to flow. So when you put a duct and attach it here, you're going to introduce resistance to airflow. Propellers hate that resistance. They will fight against it and they will overamp very quickly. So one thing you need to be aware of as an HVAC technician and mechanic is that make sure you understand the types of fans. Make sure you understand how to troubleshoot them, because you are going to troubleshoot them. Fans break, and people are usually very, very unhappy when fans break and you come and say, okay, the motor is burnt out. You replace the motor and it's burnt out again in a couple of days because you didn't fix the problem. You just replaced the motor. So one more time, different types of blades have different types of characteristics. This guy here, this is the propeller. They hate resistance to flow. Okay, so therefore in all applications, like if you see the applications, they are all boxed. There is no duct. Those are the louvers. They are not as much resistance as a duct. So you won't see a propeller that is duct, but you're going to see how a propeller type fan is duct. Sometimes you're going to see, innovative stuff like this. I took a picture just to show you the cutout of the motor. This is extremely compact motor. Look at the shaft here. That's the whole length of the shaft moving that huge blades. And the idea is this blue part, this blue cap, is the hub of the blades that are turning. So there are obviously, what I'm trying to say is fans are old technology, but there is always something new going on, and you have to keep an eye on things. Some other ways to look at fans is to look at the accessories that are attached to the fans themselves. So for example, what do you think this is? This component that is obviously attached to the inside of the fan there, and it is a clear plastic tube. What do you think this is? It's not a transformer, it's a pressure switch. So sometimes we are going to see that the fans come complete with necessary controls and safeties. It is also important to understand why. This is, for example, what we call an inline fan. If you have, this is 4 inch, by the way, the diameter here is just 4 inch. So if you are running a 4 inch diameter airflow duct for a very, very long distance, and whatever pushing energy source that is at the beginning is too weak to overcome the resistance, then you can add these somewhere in the middle and they will add some push and help move the air where it is needed. All right, this is another inline fan. As you can see, there are those blades here, and those blades is what we call back curved. I'm going to explain in better examples where you can see the blades. This is just an example of how inline fans can be. This is obviously a propeller fan, and you can tell that the direction of the flow is this way. What these blades are doing is they are pushing the air as they turn. They push the air against the walls, outside walls, where the air now is, it has nowhere to go but the other way. So this becomes the suction side, and the back becomes the supply side. This is typical, I would say forward curved. So I'm just gonna go back and show you guys the centrifugal blower types. Again, they can be straight, they can be curved forward, they can be curved backward, or they could simply be curved backward and have airfoil shape. We're gonna get back to that in a minute. This is what we call a forward curved fan. The forward curved fan scoops the air as opposed to the backward curved fan that pushes the air. Just wait until I show you the wheel alone and you'll understand what I mean. So this wheel, when it turns, it scoops the air, it pushes against the walls because it is using the centrifugal force, and then the air has no place but to go out through this opening. So it is simply forcing the air out through that opening. If you look closely, there is this wheel here. Even though the structure of the housing of the fan is the same compared to the one before, as you can see, this is almost identical housing, but the blades are different. Look at the blades here and look at the blades here. Okay, so we call these forward curved. They scoop the air because they have literally a scoop shape blades where they scoop the air. And this guy here simply pushes the air. It turns this way and it pushes the air against the walls. And I get sometimes the question that, okay, why two different types? Well, you need to remember that those two different types are opposite of each other. One is scooping, one is pushing the air. They are both using the centrifugal force, but they are doing opposite things, and they kind of meet the need and requirement of opposite conditions or applications. So one of the things is that this forward curved fan or wheel is lighter and it moves slower. Because at a slower pace, at a slower RPM, it can move more air than the backward curved. Backward curved has to turn twice as fast as the forward curved to generate the same CFM. And not only that, the backward curve is also heavier. You can see this is heavy, metal. Excuse me. Sorry for the interruption there. I was saying that the backward curve blades are heavier and they need to run twice the speed of the forward curve fan or the blades to do this, to move the same CFM. And why would you go and and also they are more expensive. If you see the welds here, it tells you that they are more expensive to make than the forward curve. So why would you go and make a fan that is more expensive to make, more expensive to install, and it requires more energy to run because of the double the speed and stuff like that? Well, because the forward curved and the backward curved have different characteristics. The backward curved is safer for instances of overloading. So in the forward curved fan, because the action of scooping, the more air you supply for it to scoop, the more work it will do. They will just scoop more and more air, basically. If you open, for example, the door to the compartment of the blower in a furnace, what you're doing is you're allowing more air to go into the blower, and that forward curved wheel is just going to scoop more air and it will overload. That doesn't happen, I would say, not as much in a backward curved fan, where if it is given more air or less air, it doesn't matter. It has a cap, it has a ceiling of energy consumption that is not gonna break through that drastically. So the two are necessarily different and opposite, and they serve different application needs. This is another angle for the forward curved. And you can take a minute or stop the video and try to see what type of wheel is this. So this would be either forward curved or backward curved. If you want to take a minute to think about it, you can stop the video. However, when I look at the direction of the flow, I see that this is moving like that, and I can tell you it is pushing the air. Okay, it is not scooping the air. To scoop the air, you need to have scoop shape, blades like that. All right. So this is, as I said, easier to make. Look at it. It's just punched through, and I'm saying easier to make compared to the backward curved, not easier to make in general. So, but it is sometimes not safe to use in applications where you could possibly open up a space and provide it with more air, and then it will overload. Another example of what do you think this is? Well, if you look closely, shape of a scoop, it is scooping the air, so it's forward curved. This is another, what do you think this is? I think it's hard to see, but I would say this is forward curved. I might be mistaken here. I'm going with forward curved. And apparently this is used for gas fireplaces or inserts where it can circulate the hot air around the gas insert. I'm not entirely sure about this, but this is what I heard from another student. As you can see, what is this? You can stop the video, think about it, but you should have a good feeling of what this is. There's no, look at the blade here, there's no curvature enough for it to scoop the air. It is technically blowing the air by, pushing it around and creating that centrifugal force. Again, you see this? The blade is actually completely straight. The blades are completely straight here. So they wouldn't scoop the air, they would be pushing the air. Also, if you look at the direction of the flow and the blade, you would, and if you can use your imagination for this purpose, you can tell that it is, pushing the air inside those, inside the volute here. This is what I was talking about before, where if you have a propeller, this is like a propeller fan, and this fan is actually designed to be ducted. So the propeller doesn't like to be ducted, but you could design it to be ducted. As you can see, the blades are pretty short. Still, they have a big motor sitting on top. So that tells you even these shorter blades will require a lot of force. These could be the vanes, actually. I'm not entirely sure if these are the blades. This could be the vanes. I hope I'm not giving the wrong information here. So this is another propeller fan, and it is also, well, this is a smaller size, just 4 blades, and they are, shouldn't call them plastic, apparently. They get offended, maybe. You should call them high performance composite blades. So as a review of all the blades that we talked about, remember for again, this is in reference to the blades that are centrifugal and axial. Okay, just in reference to those two. Remember that you have the backward curved, okay, which is pushing the air. You have the radial, or in our book it says straight, because this is just straight like that. And it looks like a diameter or a radius. And I call it a paddling, wheel. This is just a paddling wheel, if you ask me. Not very efficient. This is the forward curve, which is in this image. The curve is the opposite side. It should actually, the curve should go the opposite way. Then the airfoil blades. Airfoil is simply referring to the width that changes as you move away from the shaft. Okay, and then you have the three axials. Vane axial, there are the vanes here, but it also is propeller without the vane, which is called tube axial, and then just the propeller itself when it is not boxed in any way, that is ready to connect to ductwork. So those are the different types that I saw on the CMPX show. And in your book, as I said, there is the axial fans and there's the centrifugal blower, and they are described in different ways. So let's see how they are described in the book. You can open your book to unit 24, that is. You can open unit 24 to chapter 2 and see what I'm going to talk about. Maybe you can highlight the important parts. All right, so for the forward curved blades, blowers with forward curved blades travel slowly. I should say they have a slower RPM or lower RPM, as we talked about. They are less efficient than backward curved. Actually the most efficient is airfoil blowers. And the problem with airfoil blowers is that they are expensive to make and design. That's the only issue with them. There is nothing else. These are literally, one size fits all. There's no shape difference in forward curve. They are all the same shape. It's just that you can make them longer, you can make them shorter, and that's it. So this is one thing. And then forward curved blades can overload the motor if static pressure increases, are inexpensive, are slow moving, so bearings are and the shafts are small, so less wear and tear because it's moving slower, can operate at wide range of static pressures. All right, so let's have a look at the backward curve. Backward curved or backward inclined, both same meaning, is slightly less efficient than the airfoil. So you have the airfoil being the most efficient, and then the backward curved, and then the forward curved. Backward inclined blowers move about twice as quickly as forward curved ones do, obviously, to do the same work, because of this they require a larger shaft and a larger bearing. So again, not only more expensive to make, but it's more expensive because it requires larger shafts and bearings. Airfoil blades, they are the aerodynamic type of blades. Again, they are the highest efficiency, but unfortunately they are more expensive to make and install. They consist of 10 to 16 blades of airfoil contour, curved away from the direction of the rotation. Air leaves the impeller at a velocity less than the tip being at this here. So the velocity is different than the RPM. I don't know if this is important or relevant here. And then the tubular centrifugal blower. So you can install these blowers in straight line ducts. I have seen these in underground garages where, so one example I know is if you go to watch Leafs games downtown Toronto, you're going to park in maybe 5 stories underground, and well, how are you going to ventilate the air that deep underground? You need something like this that is ducted all the way to the outside. So um, now we're going to move to the last topic of airflow, which is Pulley RPM formula. And for Pulley RPM formulas, you probably need a pen and paper just to take notes. There are a few important things that we need to talk about, but I'm suspecting that some of you will want to or benefit from writing it down. We usually, when in a G2 training, usually Pulley RPM formulas are about 2 pulleys like this. So this is the motor, this is the motor pulley, that is, and this is the fan pulley, and there is a belt, you know, driving the fan pulley like that. And if you look at the motor pulley, something interesting is in here. There are threads where you can, if you undo this screw, you can rotate this part, this face of the shaft of the pulley, while the other face stays stationary. Let me give you another, maybe clearer image here. So again, when you loosen this set screw, this half of the pulley can turn and move. So if you turn it in this direction, it will move away from the other part. And why does that matter? When it moves away, we call it opening up. When it moves closer to the other part, we call it closing up. And this is exactly why that happens. If you look at the diameter, and if you think about this belt being seated here, so your diameter will be all this, okay? The diameter of the pulley, effective diameter of the pulley will be this. But once you start moving this piece away, so I'm just gonna try to annotate here. Once you start to take this piece and move it away by turning it as I described, right? What will happen is you're going to increase this distance. This will increase. And when it increases, this will fall down because of this shape of a V shape of an opening. When you increase the distance between those two faces, this will fall down. So now suddenly your diameter is smaller, basically. That's the whole principle of it. And sometimes you get, we call these, by the way, make sure you remember, this is called adjustable sheave. And they are usually or typically on the motor. Rarely you are going to see adjustable sheaves on a fan. It's not impossible, it's just rare to see that. All right, so you can see that this is for 2 belts, this is for 1 belt. And again, closing up means that you are making this distance smaller, so you are increasing. So let me write it here. Closing up makes the diameter larger because you are making this distance smaller, then the belt will have to move up and increase the effective diameter. So let's have a close look at the Pulley RPM itself. This is what we call the motor pulley because it is usually smaller. And this is what we call the fan pulley because it's usually bigger. And then the belt between them. So what are we looking for? We're looking for the diameter of this pulley and the diameter of this pulley. And we're looking at the speeds. So there are two, I would say, expressions of the same exact formula that you need to remember. Either the RPM of the fan multiplied the diameter of the fan equals to the RPM of the motor multiplied by the diameter of the motor, or the RPM of the fan over the RPM of the motor is equal to the diameter of the motor over the diameter of the fan. Depending on what you get, what question you get on the TSSA exam, you're going to use either or. Now, let's talk about rule number 1. Rule number 1 is when both pulleys have the same diameter, then the speed of the fan is equal to the speed of the motor. This is rule number 1. You need to remember those. All right, so let's have a look here. We're saying that if this guy here is equal to this guy here, the diameters are equal or the same, then in a mathematical expression, they will simply cancel each other out, and those two will be equal to each other. So when you have both pulleys the same diameter, then the fan speed equals to the motor speed. That's very rare. Usually the motor speed is too high for the fan, therefore we have a disparity in the size. Rule number 2. Increasing the diameter of the fan will decrease the speed of the fan. All right. So sometimes people can remember this, like verbally, and that's fine. If you can remember that like that, that's perfect. I cannot, so I have to make a way for me to remember. The way I remember stuff is that, for example, an equation means that on both sides should be equal values. That's what an equation means. All right. So what we're doing is we're changing the diameter of the fan. So we're increasing it. So when this goes up, right, diameter of the fan goes up, this is the same, this is the same. Okay. So on the right side, everything is the same of the equation. And suddenly we increase the diameter of the fan. What needs to be done to the RPM of the fan to balance out? It needs to drop. This is how I remember stuff. Again, if you can remember it as an expression like this, good for you. But if you can't, maybe this will help, or even better, if you have a better way to associate the concept with shapes and rules, then good. All right. Rule number 3, the final rule, is increasing the diameter of the motor increases the speed of the fan. All right. Again, on both sides should be the same value, keeping the same value on both sides. The first is increasing the diameter of the motor. So I increase this. All right. That's good. So this is the same, obviously, and this is the same. What should happen to this? So the two sides of the equation are the same. If this was for example, a scale like that, right? If you increase the weight here, you should increase the weight here to make them equal. So this goes up. I hope that makes sense. Those are the 3 rules of RPM and fan speed. So let's start with questions. I'm going to ask you a question, and this is repeated. That's fine. Here's the first question. An adjustable sheave pulley is mostly used on A, B, C, and D. Please stop the video and answer this question. And the answer is motor shaft. This is typical. Motor shafts typically have adjustable pulleys. I suspect that's because the adjustable pulley can make only small changes, and when you're changing a little bit on the smaller pulley, you're making a big difference on the bigger pulley. That's my suspicion. All right, next question. How is the delivered air volume adjusted? So if you have to adjust the air volume, if a belt drive fan motor is being used, how would you go and change the air volume? Meaning delivered air volume means CFM, by the way. The flow rate. All right, you can stop the video for a second and think about this. And the answer would be not A, by adjusting pulley tension and supply voltage. Not really. Those are not contributors to the speed. By adjusting the pulley or changing the pulley size on the motor or on the fan or both, that makes sense because this is what makes this. Okay, changing the pulley size by either changing the pulley or adjusting the pulley. That's actually a good choice. By adjusting the motor dimmer switch. Okay, hopefully not. We don't call it a dimmer switch. We call it an inverter, and it's a hell of a more expensive device than a dimmer switch. By adjusting RPM of the motor, no, we don't do that. We don't adjust the RPM of the motor. The motors come in usually 1720 RPM. This is so typical. Of course, there are the 3600s and there are the slower ones, but this is the typical RPM of a motor that you're going to see, and we go in length to not adjust that, and so D is incorrect, and that makes B correct answer. Next question. If a motor pulley is twice the diameter of the blower pulley, the blower speed would be A, B, C, or D. Please stop the video and think about this for a second. Right, so according to the second rule, we know that increasing the motor pulley size will increase the blower speed. That's the second rule. So increasing the motor pulley twice of its original size will increase the blower pulley twice. That makes the D as in David the correct answer. One last question here. A furnace has a belt-driven indoor blower fan. To increase the furnace blower speed, what do you do? A, B, C, or D? And the correct answer would be, okay, let's have a look here. A belt-driven indoor blower fan increase the furnace blower speed. So we know that to increase the blower speed, we need to increase the diameter of the motor. That's also one of the three rules. To increase the diameter of the motor, you have to close up the motor pulley. So this is increasing the diameter of the motor, and this is decreasing the diameter of the motor. Okay, so you need that. You need to do that to increase the furnace blower speed. All right, so that brings me to almost the end of the Pulley RPM formula. What we're going to do is in week 13, we're going to make a review of all the airflow topic, and then we're going to, after we do the review, we're going to take that test 3 online, and then I will post test 14 based on everything else that we have studied in this course. We might not have enough time to do all of heat transfer, but we're going to do a little bit of a heat transfer as well. So I guess I'll see you on in week 13.